All right, let's go ahead and get started. So today we are on lecture 11. Okay, so last class we talked mainly about kind of the theory and concept behind causality and running causal models. We kind of ended on drawing these directed acyclic graphs, right, DAGs, as a way to sort of set up the framing for our causal models. And so today we're going to continue and then focus specifically on tools in which we can start to actually estimate and quantify the sort of causal relationships. So there's a whole sort of world of possible tools to use. Today we're going to kind of cover, some of the more commonly employed tools. Often a lot of the more complicated tool sets are built off of the sort of premise that these tools will help you develop in terms of skills. So let's get into it. So tools for identification. So one is fixed random effects. Two, differences in differences. And three, we'll look at instrumental variables. Okay. Not sure why there's these boxes around here, but okay. So we're going to start off with fixed effects. So this is a very powerful method that allows us to control all variables whether or not you observe them, as long as they stay constant within a category. Okay. So, what does that mean? So let's consider an example here. Where we want to understand the causal linkage between weight and exercise. All right, so I need your guys' help here. What are possible co-founders or confounders to this particular setup? Like, do we think that there are other things beside how much we exercise that might influence our weight? No. What was that?
How much food you eat?
Okay. So let's say plus diet. What else? Actually, I'm gonna put this in a separate. I'm gonna put this over here. So we'll say diet, height, great. Anything else? Any other factors we think might influence someone's weight? That's it. Only your diet and your height. What was that?
Like your health.
Your health? Okay. Sure. Money, income, sure. Put dollars. Age. Okay.
Genetics.
Yeah, okay, genetics. Great. So basically, there's like a whole slew of things, and as soon as I probably say, okay, I think that's all, we've got them all, you guys could probably come up with a couple more, right? And so if we're doing this properly and we kind of want to understand this effect, well, you may have this issue where we have, okay, so if we draw our causal diagram, we have, oh, I put the wrong one there. Exercise going to weight. And so actually, everything that you guys listed, these are factors that are related to the individual in question, right? So I'm just going to call these individual factors. And unfortunately, we suspect that that may be kind of a different pathway that influences the weight, right? And so we may have measurements of exercise. So you have variation in the amount that people exercise, and then you observe variation in the weight of a bunch of different people. But you may have individual factors which are also varying. And so it's hard for me to suss out what effect exercise has on weight when you have all these other things. And so ordinarily, we would need to control for all of these, right? And so you would want to include all of these other variables in the regression, except that, as I was saying, the list is probably endless, right? And we may even have a pathway like this, right, that leads us to weight. So how can we deal with all of these individual factors? So a couple of ones that I'll just note here, just because that's the ones that I came up with. We have like race, right? So that'll be kind of connected to genetics in some ways. Gender, who knows? It could be something as inane as like your birth city, your amount of education, and on and on and on, plus our unobserved term. So there may even be a bunch of things that we aren't able to measure and see. So all of these guys are kind of generically under this individual factors. So let's now suppose data are collected across different individuals and across time. Okay, so let me draw maybe like an example of what a table might look like. So we have a bunch of different columns. So we're going to say I. This might be an index for a particular person. T, their weight, exercise, race, gender, birth city, and so on, right? It could include, a bunch of the variables that we talked about up here as well. Okay, so let's say for individual 1, we have 3 observations that we got in time 1, 2, 3, and they have some weights that we observe A, B, C. They do some exercise D, E, F. Okay. Does the race of this person change over time? No, right? So I'm going to put, let's say, x1, x1, x1. We're going to assume the gender stays constant as well. So here we're going to have y1, y1, y1. The birth city stays the same, z1, z1, z1. Okay? And we're going to see kind of the same thing as we collect data from other individuals, right? So I'll just kind of fill this in really quickly. So for individual 2, we observe at time 1, 2, 3. And they have some weight that varies. So there's variation in the weight. There's variation in exercise. And then across these things, they are again fixed. And I'll do just one last one, but you guys should get the point by now. M, N, O, P, Q, R, and then X3 for race. Y3 for gender, and Z3 for birth city. Okay, so what you can see in this data, right, is that there is a whole set of data that are the same for each individual I. And so you observe variation between individuals, but you have groups of data within the individual that doesn't vary. So the idea is fixed effects captures this plus all the unobserved terms that don't vary over time. Okay? So, looking at this particular example, for all of the variables that were selected earlier here, which ones would qualify as being captured by the fixed effects? So height definitely, well, okay. I guess if these are adults, then we could maybe say that the height isn't changing over time. If these are children where you're growing, right, in which case you have now height variation within the individual, then you would need to explicitly include that as a control variable, right? But if it's something that's not varying across your dimension in your group, then the fixed effect should effectively capture it, right? So height, let's say, is definitely something. Genetics isn't going to change over time. And the degree to which your individuals are having constant diet, health, if their income isn't changing, those could potentially also be captured by your fixed effects. If you do suspect or observe variation in these across your individuals, right, then I would want to explicitly include those as variables outside of the fixed effects, because we assume that they may have an influence on weight, right? And age definitely changes over time. So, if you're doing, I guess, multi-year panel studies, then age would be something that you'd want to include as well. Okay. So there are some kind of exceptions here, but if you think about the sort of broad set of like just in generic individual factors that we would have to try and capture, the fixed effect is really powerful, right? Because it's just able to get a lot of those effects without you explicitly needing to figure out all the things that are related to an individual. All right. Okay. Does anyone have any questions about that? Any confusions? Okay. So, now that we have this information, how do we actually implement a sort of fixed effects? So, there are two ways to do this commonly. And I should just mention this is kind of like the general, the general approaches that people often take. So one is demeaning variables by extracting the within variation. Okay, so this is YIT minus YI mean equals beta 0 plus beta 1 XIT minus XI average. Okay, so basically the idea is there's a person with some amount of weight, right? And there's variation in that weight. We take the average of that and then we just subtract that away so that only the variation that we observe across time is left, right? And so essentially, let's zoom in here. You're basically doing something like, I'm changing the column values from ABC to, okay, so weight to demeaned weight. So this is ABC, and now you would do A plus B plus C divided by 3 minus, or other side. This would be A minus this, B minus this, and then C minus this, right? And so the idea, right, is that like I equals 1, so person 1 has some kind of average weight that is a sort of result of all of these individual factors. We get rid of that variation between individuals that is explained by all of these things, and the only thing remaining is the variation in exercise relating to the variation in weight that is demeaned. Okay? Any questions about that? All right. So that's one way of doing it. And the other way is to add a binary control variable for every individual. So yit equals beta 0 plus beta 1 xit plus beta 2, where we have our control variable for I equals 1 plus beta 3, control variable for I equals 2, beta 4, I equals 3, and so on and so forth. So you're essentially adding a dummy for every individual. And that's going to give, if you think about what's happening qualitatively, you're going to give a new, essentially, slope for every individual. And that's actually doing the same thing as technique 1. So what ends up happening is your beta for the variation in exercise is actually going to look exactly the same. You will have a whole bunch of other variables in the equation that describe kind of the effect of the individual factors on weight. But then the final causal variable that we're interested in, which is the exercise, that's going to look exactly the same as 1. Because essentially what we're doing is we're just attributing the variation in slightly different ways of the individual factors on weight. Okay? Any questions? Oh, sorry, I forgot to mention. So we do have, you also have to demean your exercise variable. So we would do the same process as over here for exercise as well. Okay. I will mention that this one, the second version, is probably more rare. This is more rare, especially if you have many individuals, right? So if you have 1,000 individuals, you would have 1,000 of these dummy variables. Are you really going to bother interpreting all of those coefficients, right? The thing that we really care about at the end of the day is the causal mechanism, and that's what we're trying to identify. And so oftentimes the first approach to this is cleaner because you don't have all these other variables that you need to deal with. Okay? Questions? Okay. Let's look at a couple of examples. Okay, so we're going to use a couple libraries. I'm drawing this directly kind of as an example from that causal textbook that I was telling you guys about. So they use the tidyverse package to do some of their data preparation. And they also have some data which we'll get from a different library. So we're going to load in a couple new libraries here, which you guys may have to install. Okay, so I'll use tidyverse. Model summary is a nice library that will produce some kind of like nicer looking outputs for our regression tables. We'll see this in a second. Fixed estimation, that's one of the packages we can use to do some of these identification tools. GMM we've used before, and then causal data is where we're going to get some of our data sets. So we're going to start with our example of fixed effects. We're going to do GM, and we're going to draw from causal data. There's a data set called Gapminder. So if I look at this data, okay, what does this look like? Okay, we have country, continent, the year, life expectancy. This is life expectancy at birth in years, the population, and then GDP per capita. So we're interested in understanding how GDP, well, okay. Let me see if that's the right one. Yeah, we are interested in how GDP per capita influences your life expectancy, right? And so GDP is one attribute of the country, right? That's essentially an indicator for like economic strength. But there are many other things, right, within a country that may affect someone's lifespan. And so the idea here is to leverage the fixed effects of the country in order to control for other factors related to that country that may influence people's life expectancies. Okay. So what we're going to do is manually do the demeaning. Okay, and so I'll show how we do this. And this is, again, using the dplyr package, which we haven't talked about before. So I'm going to put in sort of extra notes so that we understand what's happening in each step. Okay. So this is like a, I think they call this a pipe. It's a way that we're specifying to do a series of operations on our data. So first thing, we're going to put GDP per capita in log format since it's very skewed. So we're going to mutate log GDP per cap. And that's going to be like so. We're just logging that. So we're creating a new column called log GDP per cap, which is just doing the log of the GDP per cap column. And then we want to perform each calculation by group. So that first step, so you're literally doing this in order. So the first step, we've created a new column. And then what I want to do is for every country, I want to do some sort of operation. And that operation is, actually, you guys tell me in English, what am I trying to demean and how am I going about doing that? What do you guys think? So remember from the notes, there's two things we need to demean. Any ideas? What is our y variable? Life expectancy. So we're going to demean that. And then what was the thing that we were saying relates to or causes your life expectancy to change? There's only like 3 variables in this whole data set. Yes, GDP, great, right? So we need to demean life expectancy and we need to demean GDP, and we have to do that within the group, right? So to set us up, we're gonna do this procedure called group by, which means that the following operation is just going to be applied to the group. So get within variation by subtracting out the mean. So mutate. We're going to do life expectancy within, like so. And that is life expectancy minus the mean of life expectancy. Okay. Pretty straightforward. And then we want to do that for GDP. So log of GDP per cap within is equal to log GDP per cap minus the mean of log GDP per cap. And that's it. We no longer need the grouping. So here I just ungroup. And that's done. So you can run this. And what we will see in this Gapminder data set is I now have 2 extra variables, or actually 3. We have the logged version of the GDP per capita. We have our life expectancy, and then we have life expectancy within each group, and then that's demeaned, and the log GDP per capita that is demeaned for the values within each group. Okay. So we can analyze the within variation. We can do this. M1 life expectancy within. Okay. And then we can use their fancy new, or not new, but the model summary. So M summary is the thing that makes it a little, you get these cleaner table outputs. So I'll show what that looks like in just a second. We have to specify our significance levels. All right. So I run these 2. Oh, what happened? Log GDP per cap within not found. Oh, I did not put the underscore here. All right. Yeah, so they give you a little nicer kind of visual table here. Okay, so in this case, after we've demeaned everything, we see that there is this variable log GDP per capita within that is describing the specific variation that we observe, changes in GDP related to the variation within each group on lifetime, means that as our GDP per capita increases by, GDP per capita increases by 1%, then do I have this backwards? Your years go up by 9, or is it the other way? It's a log change. Yeah, I think that's right. Yeah, so a 1% increase in GDP corresponds to a 9.8 year increase in your lifespan. Okay? Any questions? Okay. We can also do this the other way, right? So this was the d-mean version. We can also, so this whole thing is by FE by d-meaning. We can also look at FE by adding a dummy control for each group. Okay. So here we simply include a factor variable in the model to get it turned into binary variables. You can use factor to ensure it's done properly. So M2, we will do life expectancy regressed on a dummy for every country. And then we just need to log our GDP like we did with the other model. Oh, oops, LM here. And I'm just going to copy and paste this guy here, so we'll have the same thing. M summary of M2. Okay. So I'm basically running the same thing, except this time I'm doing it with dummies instead of doing the d-meaning. Okay. So before I hit enter, recall that the answer for our coefficient that we're interested in is about 9.769. Okay? Let's do that. Okay, and so what you see here is that every individual country has this different intercept with their kind of baseline for life expectancy. Okay, so every country is going to have this. And this information can be useful, right? If you're interested in understanding like the average effect of a country on someone's lifespan, this is essentially what these results are telling you. And if I go all the way to the bottom, we will find the one that we're particularly interested in, right, is that causal effect of GDP per capita on on life expectancy, and here we find the exact same result. So so a 1% increase in GDP per capita leads to a 9.769 increase in years of your life expectancy. Okay, so exactly the same, done in two different ways. Okay. And as I was mentioning, the demeaning version is much more common because oftentimes we don't necessarily care about all of these other coefficients, right? And this can get really big if you have many individuals, right? Here we have like 200 countries, so already it's a little bit unwieldy, but there is some useful information being captured there if you care about that. All right. Any questions? Okie dokie. In which case, we will jump back over to talking about our next one. Okay, so another technique, pretty powerful technique, to think about this is something called differences and differences. And so actually, before I get into detail about this, I think you're going to see a common theme amongst the tools that are being used for identification, which is related to what we were talking about with fixed effects, which is, there's like weight and exercise. We want to learn what exercise effect is on weight, but there's all these other factors that we may have to include as confounders, but we may be limited in our ability to do that. That is, I think, one of the primary things that all of these tools are helping to work against, is like having to, or techniques to avoid or dealing with all those confounders kind of simultaneously. And differences is a very powerful way of doing this. Okay, so this is a method of controlling effects by observing groups undergoing treatment versus groups that never undergo treatment. Okay. So typically we think of like some treatment effect as like some kind of intervention measure. That's often the type of that's often the thing that you want to measure the effect of. So maybe I have something like treatment going to outcome. And there may be a whole bunch of other things going into outcome that we don't control. And so what I want to do is I'm going to introduce a group that affects the treatment, right? So there's a group, and depending on what group you're in, you get a certain treatment. So we will note that adding group adds a backdoor. And we're also, it doesn't have to be time, but oftentimes this is one of the most common dimensions that we use in our differences and differences. Okay. So I have two backdoors that I have to deal with, right? So one, I'm going to isolate the within variation for treated and untreated groups. So this will close the back door. And then I want to compare variation in treated group to within variation in untreated group. And so this is where the time dimension comes in. You have an untreated group, and you observe what happens before and after the intervention. So in your, essentially kind of like in a control group. And that helps to close the back door for your time differences. Closes the back door for time. Okay. This.
Quick question.
Yes.
So for number 2, you're comparing like before the treatments and both groups.
Yes.
For the treatment group versus the untreatment group, before the treatment happens, or the time, or.
Yep.
Okay.
So you're saying, and I'm going to do an explicit example of this in a second so we understand. But the idea is you have a treatment group and control group. You observe the differences across these for the group backdoor, and then in number 2 you have the control group, a treatment happening, and then what happens to the control group, that change over time compared to your treatment group, the treatment happening, and then post-treatment over time. And the idea is like, actually, let's just do the example and we should be able to see. Okay.
But also quick question, is the backdoor like treatment from group to outcome, or?
It is the difference between it's the difference between the outcome from the treatment group over time versus the outcome over time for the control group. It's that difference. Yeah. Yeah, so I fully acknowledge this. This can be a little bit confusing, but let's look at this example. So we are in 1849 in London. I'm going to call this Area 1, and then we're going to do London Area 2. Does anyone have any idea what's happening in London in at this time? Any historians here? Yeah, so there's a big cholera outbreak. Okay. And so death rates were actually relatively high at the time. And there was a suspicion that cholera, it may be related to water sources. So there's a famous intervention. So we're going to have a look at how death rates change over time. Okay. So Lambeth intervention. And what they did was they shifted the water source upstream so that that I guess like people weren't ingesting recycled. Well, not recycled. They weren't downstream. Though the water sources weren't coming downstream of like sewage sources. So this is a shift in water source upstream. And then in this area, there's no treatment. Okay? So why is it that we do differences in differences where we are interested in understanding not only the difference happening from treatment to in the treatment group for pre-treatment to post-treatment, but also what the control looks like in the absence of treatment? Suppose that we observe a big drop in deaths in London Area 1, but we also observe a big drop in deaths in London Area 2. Then how do you know that the drop in mortality rate is related to this treatment effect of moving the water source and decreasing cholera? How do we know that it's not that compared to in London Area 2 where there was no treatment and deaths dropped, right? Then you would be saying, oh, actually, there's something else that happened at this time period that wasn't the intervention, because we see decreases in the baseline. And so the control group is really important to like properly calibrate the actual effect of the treatment, because you have two groups or two areas, right? London Area 1 and London Area 2 that look pretty similar. And so you are controlling for the variation that happens before and after your treatment, in addition to the treatment itself. So we would do something like, or if we look at the data, it might look something like this. So death rates in 1849, and then death rate in 1854. Okay. So here we have our non-Lambeth group. That's our control group. And then we have our Lambeth intervention. So here, prior to the intervention, 134.9 and 130.1. Right, this is area 2, this is area 1. Okay. And actually in area 2, 146.6. And in area 1, it went down to 84.9. So we would say the true effect is that it's not only this difference, right, it is also the difference attributed over time here. So 146.6 minus 134.9. Oh yes, thank you, solved that for me. 11.7. So there's an increase of this, and then we have 130.1 minus 84.9. That's equal to 45.2. So the true effect of this would be 56.9 decrease in death rate as a result of the treatment. Okay? Everyone follow along? All right. So in a regression setting, our kind of how-to, we can do y equals something generic like this, where you are explicitly controlling for each of the groups. So this is, this would be a dummy for the group. This would be a dummy for time. And then you have a coefficient on the treatment. So this is with two groups. So this ends up being the same as y equals beta 0 plus beta 1 treated group plus beta 2 after treatment plus the interaction beta 3 treated group times after treatment. This is actually just known as two-way fixed effects. Differences and differences. Because in two-way fixed effects, we essentially are having a control for two different groups. One group being, in this particular example, the areas, and then one group being the time. Okay? So differences and differences actually is somewhat related to our fixed effects that we talked about earlier. Okay, any questions? No? Okay, then let's jump on over to R, and we can do another example. Okay. So we're going to do difference in difference, and we're going to look at a data set called OD. Stands for organ donations. So let me give kind of the setting for this. So most states in the country, if you want to donate your organs, it is essentially an opt-in program. You have to choose in some form or other to say, yes, I want to be an organ donor. Typically speaking, opt-in programs, the baseline tends to be the highest for the default category, right? And so that means in most places in the country, if you choose not to opt in, that means your default is you are not an organ donor. The state of California was interested in kind of changing the baseline structure. So it's called active choice. So it's not quite a opt-in, opt-out. When you sign up for a driver's license, you get asked whether or not you want to be a donor, and you can still choose yes or no, but now the no option is like actively checking the box, right? And so that helps to eliminate the baseline. You actually actively have to make a choice. And the idea behind that was active participation is an implicit way we thought of maybe increasing organ donation rates, right? Okay, and so you're essentially forced to choose as opposed to having to opt into the program. And so we want to understand whether the switch to active choice is actually something that will affect the rate at which people are enrolled in being organ donors. Okay, so this happened in this program kicked in the third quarter of 2011 in California. And so all we want to do right now is essentially create a dummy variable to indicate that that the treatment happened. So if we look at this data, looks something like this. So we have the state, the quarter, the rate, the organ donation rate, and then the quarter number. Okay, so what we're going to do is create a treatment variable. So I'm going to do my little pipe thing again, and we're going to mutate, and we're going to create something called treated, where that happens in the state of California, and quarter in 03 to 11. Q3, not 03. Quarter 3 of 2011, quarter 4 of 2011, and quarter 1 of 2012. And I think the data goes up through quarter 1 of 2012. So if I do this and I revisit my OD, it's false everywhere except for the state of California in those couple periods that we specified, right? And that is essentially our treatment group. So we're going to do clusters, fixed effect by default, no adjustment necessary. So we will use this package called FEOLS. In the previous examples with fixed effects, we demeaned the data manually, but you don't always need to do that. There are packages that will do the groups, that you can specify the groups, and then it'll take care of everything for you. So FEOLS is one of those, so fixed effects of ordinary least squares. And we're going to do a rate, the donation rate regressed on the treatment group. And then we will have fixed effect groups of state and time. And I'm going to do the same summary thing from this model here. Okay, actually we don't need to zoom in or anything. Okay, so what is this essentially telling us? What does this coefficient say? Help me out here. What is our treatment based on my description of this problem? It is the application of active choice, right? So what we're seeing from this result is that actually when we implement active choice, the donation rate actually went down a little bit, or the rate at which people volunteer or opt into being an organ donor decreased. So maybe it had kind of a countervailing effect than what our sort of policymakers had intended. Okay. I can show so this is a visual representation of this effect. So what's happening here? So in the very first plot, this is just essentially the raw data. In the solid black dots are organ donation rates in the state of California. And this vertical dotted line indicates when the active choice program was implemented. And so that is our treatment. All of the other dots that you see in this plot, the sort of light gray ones, those are all the other states. And these are acting essentially as controls. And maybe it's a little bit hard to see, but this dashed line here indicates what the average organ donation rates were in other states prior to and post-treatment. And so there's actually a very small increase in donation rates after the treatment for other states. And so there's just over time, something's happening to bump up that organ donation rate slightly. And so we would expect, had we not applied this treatment effect to California, the assumption is that California would also see like a commensurate increase in their organ donation rates just over time. So you calculate the difference between the after and before for both California and on the state averages. That's what's happening in B. And then you want to kind of subtract that from both sides so that whatever happened in your control group, you apply to your treatment group as well. And then you observe the difference before and after the treatment, and it's actually magnified. So we see there's actually a decrease in California afterwards and an increase everywhere else. We apply that increase to the final result of the California treatment, and that actually magnifies the decrease in the treatment effect loss or decrease in the organ donation rate. Okay? And yeah, that is differences in differences. Any questions? All right. So, touching on this kind of theme of lots of unobserved possible confounders, right? The idea is that we think a lot of those confounders will apply to other states, other groups, and that's the power of the difference in difference is it allows us to sort of automatically control for all of that potential variation that's happening between or within the groups. Okay? So let us move on to the last one we'll talk about today. Which is instrumental variable. This is a variable that affects your treatment and affects your outcome only through the treatment. Okay, so in a causal diagram, this might look something like this. And in this particular diagram that I've drawn, right, we have our fundamental issue that if I wanted to explain the causal effect of X on Y, I have unobserved variables that are acting as backdoor paths that confound my ability to say it is actually X leading the effect of X on Y. So the idea is we introduce an instrumental variable like so. And it turns out when you do this, this can remove any part of the outcome that is not explained by the instrument. Okay? So it's really important that it can only affect the outcome through the treatment. So what does that mean? That means this. If that was an arrow, that would be invalid as an instrument. If this is an arrow, it would be invalid as an instrument. If this was an arrow, that would be invalid as an instrument. Okay? So the most important thing is that the effect that we observe, that we're interested in, the IV, the instrumental variable, can only affect it through our treatment. Okay? Any questions about this? All right, so let's do an example of this. I want to look at BMI, and I am interested in the effect of smoking on BMI. So this is our treatment. And so the idea is if someone smokes more or smokes less, how does that affect their BMI? That's body mass index for those who aren't aware. So what are other things that might affect our BMI? There could be a whole number of potentially social demographic factors, right? So maybe income or age or gender, whether you are pregnant, right? All of these things could potentially, and we'll say one more, education. So all of these can potentially affect your BMI. And so I'm a smoker, but then there's all this other variation that could be happening that could be explaining BMI. And in fact, we have this problem where there's probably a bunch of unobserved variables that will affect it too. So we have our classic issue, potential confounders, and we have to deal with some way of explaining away the variation that's contributed by the confounders. Okay? So we want to come up with a instrumental variable here. And we need to come up with something creative, right? Because it has to be something that is unrelated to anything else. It can only get to BMI through someone being a smoker. Okay, so let me pose a couple of potential IVs, and then you guys can tell me what you think about the quality of the instrumental variable. Okay, so one, unemployment as an instrumental variable. So do you guys think that unemployment, whether or not someone is unemployed, may affect the likelihood with which they are smoking? Yeah, probably, right? I could buy that, right? Maybe being unemployed is more stressful, leads you to smoke more. Okay, so does that mean it's a good instrumental variable, right? So we can plausibly see unemployment here. What do you guys think? Okay, thumbs up for good, thumbs down for bad. Thumbs down. Okay, I see a bunch of thumbs down. What's giving you that impression? I saw a thumbs down from you. Okay, great. So we suspect that could be the case, right? And so if you're unemployed, maybe that affects BMI directly, which means no good, right? And in fact, this could probably affect your income too, right? So it could probably go through a number of other variables. Okay, so no good. Fix that. Okay, how about if you are separated or divorced? That could plausibly affect how much you smoke, right? Good instrumental variable. I see you shaking your head. What's going on? Why is this not necessarily a good variable? Okay, maybe it affects BMI directly. Maybe that affects the likelihood that you're like pregnant, right? So different avenues to BMI besides through smoking. So again, not a good variable, or not a good instrumental variable. Okay. What about this one? Cigarette tax. Okay, so could a tax on cigarettes affect how much you smoke? Probably, right? More expensive, you smoke less. And here, we can try and think about plausible connections to our other variables or to BMI directly, right? And this is kind of where some of the art comes into play for deciding the plausibility of an instrumental variable, is you have to be able to kind of defend its like linkages or lack of linkages to other variables or unobserved variables. I don't know. Like if I was like a nitpicking economist or something, I might be like, oh, well, the cigarette tax could cause you to be so stressed that you lose weight or something, right? And in which case I'd be arguing, actually, there's like a direct effect on your BMI. But let's maybe put that aside, right? This is probably the most disconnected variable from a lot of these other potential confounders, right? And so if we are convinced that that's the case, then I could describe this as like a plausible instrument, right? And the strength of the instruments, so let me just kind of clarify this, right? So the plausibility of the instrument is related to how it relates to other variables. And so if we say that there's no relation, then it's like a plausible, it's potentially a plausible instrument. The strength of an instrument is related to this effect here. Okay, and so if cigarette taxes have a strong influence on smokers, right, that might be like a strong instrument. Um, and oftentimes the plausibility part of it is kind of the more important thing because it's just, in general, often hard to find good, plausible instruments. So in this case, we say, okay, this thing kind of passes the sniff test, right? And so cigarette taxes we're going to consider as an instrument that we can use. So I'm going to show an example of this particular problem in R in a second, but let's first discuss, what's the like procedure for implementation once we've chosen an instrument. So this is generally done in something known as two-stage least squares. So how to estimate two-stage least squares. This is also known as 2SLS. So OLS, we would have something like this, y equals beta x plus epsilon. But in 2SLS, we actually have two stages. So stage 1, we do our IB portion. So we do, so X, if this is our treatment, we actually start with the effect of the instrument on the treatment instead of the treatment effect on our outcome. So that would be X is equal to, let's say, delta IV. Delta is just another version of beta, basically. Plus here. And so if we run this regression, we can calculate the effect of our instrumental variable on X. And here we would actually need to add other controls if they are present. And we would have X hat here and IV like so. So we have our predicted X. And here in stage 2, we would have Y equals beta X hat plus epsilon. So we are not estimating on the original X's, we are actually estimating based off of the predicted X's out of the first stage. Okay? And I will caveat that oftentimes, this procedure, you can have a valid instrument, right? Something that's plausible as an instrument, but that it's actually weak. The effect of, let's say, the cigarette tax on people smoking might be really weak. And that can actually add to a lot of noise. And so your model estimate may have less statistical significance. It maybe have like a lower R squared. It may predict outcomes worse than, if you were to just run our original OLS. And that's the price we pay for trying to implement some of these causal models, right? And so really it's about trying to extract the causal effect. That's the thing that we care about the most, and getting that that coefficient, that beta coefficient, as kind of representative of the causal effect as possible, rather than just the sort of correlation type relationships that we've been talking about before. Okay, any questions about 2LSLS? Okay. So let's do our example in R. And this one actually comes from data, so I need to put this on Canvas really quick. So one moment while I upload this data. And this is just the example that we've been talking about, so we will be looking at the effect of this like cigarette tax. Okay. Okay, so you'll find a file called ps6.txt in lecture 11 files on Canvas, and that's going to contain the data that we need for this particular example. So this is our cigarette, I'll say our instrumental variable regression example. We have this BMI data called ps6.txt. It's tab separated, so I do have to specify like that. Header equals true because there are column names. And I'm going to just keep the rows that are completed. So if there's any NAs, we're just going to get rid of those. Okay, so if we were doing this as an OLS, it would look something like this. Linear model of BMI regressed on, and they squared the income and age data. It's a little bit concave, so this is a way to linearize it. And then we have a bunch of different factors for gender, whether they're pregnant, level of education, and then importantly, whether or not they smoke. Okay. And here, object, age squared. Okay, so here we run the regression and we get a bunch of results. And the effect of smoking, as you, if you're a smoker, your BMI on average increases by 0.29, okay? But we would have difficulty defending that particular effect as causal because of all of the confounders that we have been discussing. And so in order to get around that, we're going to do our instrumental regression, our 2SLS. With cigarette tax instruments. Okay, so we're going to work through this manually, where we essentially do our first stage and then run our second stage. And then I'm going to show a package that will kind of do it all at once for you. So first stage, regress treatment, which is our smoker, on the instrumental variable, which is the cigarette tax. So stage 1 model, sig tax. This is LM smoke. And then we have to include all of our other controls. Oop, wait a minute. Plus sig tax. Okay, so that's our stage 1. We could actually look at it and see what that looks like in terms of the results. And we do see that in general, an increase in the cigarette tax leads to a decreased likelihood that the person is a smoker. It's not statistically significant, so that does speak to the strength of this instrument is not very high. And okay, we're going to add into our original data set a new variable, which is going to be the prediction of whether or not they're a smoker. Like so. And so essentially what we're doing is creating the X hat. And so in the second stage, we're not going to include whether or not they're a smoker, our treatment. We're going to include the predicted treatment from our first stage. So stage 2, model cigarette tax. That's equal to LM BMI, income squared, age squared. I'm just going to copy and paste all of this. Okay. Plus smoke.iv.sig tax, which is that new variable that we created. Data equals BMI.data. Stage 2 model sig tax. Okay, great. And here you have now estimated a 2-stage least squares, and now we see the coefficient size is actually quite a bit larger. And so we're basically saying if you increase the likelihood, or if you increase by 1, smoking, the predicted value of the smoking, right, then that corresponds to some amount of increase in your BMI, and that value looks pretty different. I will note that these standard errors are not correct. The way that we've manipulated the data means that the way that you estimate the standard errors has to be different. And so we did this manually, and so there's a whole different procedure to calibrate your standard errors. We're not going to get into that, but I'll say the built-in package that does the 2SLS from start to finish for you does have the calibrated versions of the standard errors. So not something you have to worry about. This walkthrough, again, is just to make sure that we're familiar with the sort of procedure happening behind the 2SLS model. Okay, so we need library. So AER is the package that has automated IV regression applying 2SLS. So we can see what that looks like. So it uses a function called IVReg, and everything looks essentially the same. Copy and pasted all this stuff. So where the specification changes is right here. We add in all the variables, and the treatment variable that you're interested in understanding the causal effect on, the one that you're going to instrument on, comes last. And we do this horizontal line that's indicating, oh, this particular variable, you're going to do the first stage applied to it. And here, I add in all of my other variables plus my instrument. So they're all going to appear again, and then we have data as per normal. Okay, here, I'll run this, and we can look at a summary of this model. And you will see here, this effect is exactly the same as what we had done in our manual version, 1.372. But the standard error is different from this. This one is larger, right? So they've calibrated for the difference that happens when we're doing the first stage and then using the predicted values. Yeah. So at the end of the day, this ends up being a weak instrument. It's not statistically significant, but that's kind of besides the point here. Oftentimes most, kind of to reiterate, most instruments that you use are typically going to like weaken the model, unless there's like a very strong effect of your IV on your instrument. Okay. Any questions? Who's done IV regression before? Anyone? Okay. One or two. Yeah, so in general, when you're in the causal world, these different techniques are all pretty common ways in which we're getting around the idea of having to control for too many things. Instrumental variables, very common in like the econometrics field, where they do care a lot about causal outcomes. And the more you're kind of exposed in this field, the more kind of interesting, creative instruments I think that you'll see. You have to get pretty creative with them, right? You have to find pathways with which they influence certain variables and not other ones. One of the first papers that I wrote when I was in grad school was with this economist, and we had done, just to give a sense of kind of this interesting instrument, we were looking at how VMT, so this is vehicle miles traveled, is affected by changes in gas prices. You can imagine this is like a pretty interesting question. A lot of people have looked at this before, but this idea of like how changes in gas prices change people's travel behavior. But as you can imagine, there are tons of potential confounders for this type of problem. And so we fundamentally run into this difficult issue. And so we were so I went to grad school in Pennsylvania, so we had this big data set of VMT in Pennsylvania, and same with gas prices in PA. So the instrument that we came up with, right, which means that you have plus all of these confounders that could be affecting things like here. We'll call this U. the one we came up with was, what is it called? So, oil refinery shutdowns in the Gulf of Mexico due to hurricanes. Okay. And so the idea is that if a hurricane comes through the Gulf of Mexico and shuts down a bunch of oil refineries, that affects gas prices in Pennsylvania, but plausibly would not affect a lot of these other things in the Pennsylvania region that could be influencing, gas prices and travel behavior, right? So, yeah, the type of instruments get really kind of out there, and they can be pretty hard to validate and to defend, but this is kind of a example maybe of one of the wacky instruments that I've used in the past for this kind of problem. All right, I think that's it, unless anyone has any last questions for today. All right, then I will see you guys all on Thursday.